So in this module, we are going to discuss mostly linear algebra, which is about vectors, system of linear equations, and how to solve them. But before that, we'll have to build up the intuition, and these intuitions come from real life situations, and then how to solve optimization problems using these methods. And then linear algebra is used almost everywhere in every field of science and technology, business management, so it's extremely important. So here we'll discuss the basics of it, but first our goal is not to talk about the formal mathematical definitions or workings of it. Our goal is more of a computational, and that's something we emphasize a lot. Because at the end of the day, if you want to be a programmer or quantitative programmer, you should know how to program it, or know enough about the methods, what to program. So let's start with a basic intuition and build up. So usually in life we use numbers to quantify something. Say 1 apple. Or you even go to say 2.5 kilogram of something, of apple. So this is just one type of thing. What do we do if we have different things? So of course, if you add to 1 kilogram, say 1.5 kilogram of apple, another, and then you add it, then you can get 4.0 kilogram of apple. So this way of adding numbers, as long as the units are equal, works because we are talking about apples. But in real life, we need to talk about several different things. So the goal is that how do we handle more than one type of things? We cannot compare apples to oranges. So we have to come up with a mechanism, and if we do, we have to come up with the rules of the mechanism. So let's start with some simple example. So suppose I have 5 apples and 3 oranges. So now we can represent it with two numbers, 5 for apple, 3 for oranges. So what we would do is something called a two-dimensional vector. 5, 3. So you have to be very precise about it. The first one always talks about number of apples, and second one talks about only oranges. You have to keep track of it. You cannot afford to forget that. Then you would lose the meaning. So now, once we have that defined, let's see, we need a shorthand notation to represent all of this. So the way you represent these things where there are more than one quantity is a vector. So V is a vector, and you put this arrow sign. So we can call it vector V. So we can call it vector V. Right? That's how we can pronounce or say that. So it has two components. I represent it with a subscript called 1 and 2, first and second. Or you can use both square bracket or round brackets, it doesn't matter. And we might use both of them, but it's all the same. So here in our case, depending on the meaning you give, the first one talks about apples, the second one talks about oranges. Okay. So now you can also, some people like to call it, because it's in the form of a column, let's call it column vector form. Or sometimes some people like to write it in this way. It's easier to write. It's called row vector form. So now let's talk about how to add or do some operations like addition and subtraction or multiplication with these vectors. Let's start with two vectors. One is called v. I don't think I need the subscript. Okay, so v and v1 and v2. This time we call it the first component of the vector, and similarly this is the second component. And so on. Vector. Similarly, we have another vector, say w. It has components w1 and w2. Now let's give some numbers again. So now we are using v sub 1, v sub 2, or w sub 1, w sub 2. Instead of that, let's work with real numbers. Let's say v is essentially what we have is 2 apples and 3 oranges. Same thing with w. I'm just going to write in a more convenient way. 4 apples, 5. That's the fact that I'm writing w to the right of it. It means that it's the same thing, just for convenience. So now we want to add it, say this concept. So I have one basket of with 2 apples and 3 oranges, another basket with 4 apples and 5 oranges. So if I combine them, add them, what happens next? So what happens next is that a intuitive rule would be, this is a combined vector. So you took 2 vectors and created a new vector, and that is going to be your 2 plus 4. You add component wise, 3 plus 5, and that's 6 and 8. So now as a result, we are adding apples to apples, oranges to oranges. So in other words, this is essentially, what have we done here? What were we doing here? Here we are doing essentially v1, w1, v2, v2 and w2. That's all. So here adding apples. Here we are adding oranges. Okay. So now we have defined the rules of adding to numbers. Now let's say, what about subtracting? So we have to come up with a rule. Well, let's start with, again, how would it be? Intuitively it looks like we do the same thing. We do subtract apples from apples, oranges from oranges. So you have 2 minus 4, 3 minus 5, minus 2, minus 2. So essentially, if you take away 4 from 2, you are left with minus 2. Maybe you can look at it as like you have this, you owe someone. Minus means positive is for having with you. So that is so far so good. Now let's look at multiplication. So let's talk about, let's switch the color to green. Okay, multiplication. Multiplication. Okay. So multiplying. So let's try adding the same vector to itself. What do we get? So usually we do v, w if we have 2 vectors, and suppose this is exactly equal to v, the same thing itself. Then how do we add? The same rule, v1 v2, and it's the same thing over v1 v2, and then you add them, then it becomes 2v1 2v2. Well, it looks like maybe we can essentially say adding two factors means twice you do v1 v2 or 2v. So that's one natural rule maybe we can have. Maybe we can have this natural rule that would simplify. Well, if we can do 2, so that means if we can have any number c, v, we can generalize it to say that whatever that c number is, it just goes and multiplies the individual components using this machinery. If we can do it for, build up the intuition for integers or numbers like 1, 2, 3, 4, 5, why not any number? So instead, this makes it a lot easier even. So say c equal to 1, then cv in that case would be simply v, and it would be the same v1 and v2. So now, what if we want to talk about c equal to minus 1? In that case, you have cv or minus 1 times v, and you go ahead and multiply the internal numbers with v1 minus 1 v2 and minus v1 minus v2. Well, some people might write it like this. So negative of a factor means essentially multiplying by minus 1 with the components. So that's what it means. So that means this rule that we defined here, it can be called as a multiplication, but it's a scalar multiplication. A scalar means, say, a real number. It's a scalar, something that's not a vector. Scalar multiplication, you are essentially multiplying a scalar to a vector. Multiplying the scalar to a vector. Okay? So that's a rule. And we don't know how to multiply vector with vector, but that's a different thing. We'll deal with it later. But this is something to remember. Another interesting thing to note is that what about these operations we do? Addition operation. So I'm going to say addition. There is a rule, addition, or rather property is vector addition. Is commutative. So let's see. I have two factors v and w, and then I'm going to add it like this, and then v1 w1 v2 w2, and then we have essentially here added. We can reverse, you can write the same thing as, instead switch, you can write them in the opposite order. These guys switch, or these guys switch. So then I can write this as if same rule, applying the same rule, because these are just numbers, any general numbers, and you can write it as. So what we have shown is that this essentially, or you've seen, we have established this. So that means it doesn't matter how you write this first and this second, or this first, this second, it doesn't matter. They give us the same value. So this is called commutative. That means where you can interchange around that symbol, positive, or our definition is the same thing. Another thing I want to tell you is that we have done this addition as if like it came into us naturally. No. When you do addition, let me show you in this rule here. This is a definition that you have come up with. This is essentially, I'm going to write it down here. This is something, this rule that you define, corresponding numbers, these rules, these are redefined essentially. Define this for vectors. So although we are used to adding numbers used to using this plus symbol, it's essentially a different meaning it has. Maybe you could say, well, this is this kind of things that work for vectors. It's not the same as the plus sign that we are used to using with numbers. We have redefined it for this vector and then generalize it. Okay, so that's something to keep in mind. It's a more of a definition that you choose, and then you develop the machinery around that definition. All right, so next we are going to talk about linear combinations. So far we have learned how to add two vectors, and maybe we can do more complicated addition of two vectors. How do we do that? So that is going to be called, next level is linear combination. Of course, we'll have to realize behind all these definitions there has to be some usefulness of conciseness. Maybe it's easier to represent or things like that, right? So now, what is the idea of this? You want to create out of simple definitions more interesting, maybe complicated definitions that you can use to explain or solve other problems. So that's kind of a goal of building up. So now we combine the ideas of vector addition. We will simply call addition, and scalar multiplication, we call it simply multiplication. Scalar multiplication to create new vectors. Okay, so let's define what do we mean by linear combination, and you will see that out of those two vectors w and v, or any two, you can create a whole lot of other vectors that can be generated by this. That is important to realize. So now we say the sum of two vectors which you derive by multiplying with a scalar value, which is any number, 1, 2, 3, 1.5, 6, doesn't matter, 2.1, any real number, and dw, d is another similarly real number. So is a linear combination which is also a vector, which is again a vector. Linear combination of v and w such that we say that CV plus dw can be defined as C v1 v2 d w1 w2, right? So let's see we do this. Now we are not defining anything new now. We are just following the rules that we created earlier, and then we are going to apply them. Let's see now how. So we know that we tried to add that, and simply from here I got there, from here I got here. We know this is essentially a scalar multiplication of the scalar c with the vector v, and we know the rules. We saw it a minute ago. You simply go and multiply it inside, put them inside. So CV1, CV2. So we just are following the rules mechanically. Anything we define, we can use it. When you want to use something, you have to make sure that it's well defined. Otherwise, you can't use it. Or create your definition so that it makes sense in the machinery. So now we are stuck with these two. But we know how to add two vectors. See, how to add it. This and this. 1, this 2. Let's try adding. So we know all we do is add apples to apples, orange to orange, or however you interpret, but similar position to together. So now CV1 plus dw1. CV2 plus DW2. So that's your new vector. Those are the components. Okay. So, for example, we can think about that these vectors as like two-dimensional representations of some vectors on the plane. And we will pick up two examples and explain you this. Okay. Let's see which one we should explain. First, maybe we should see some examples of linear combinations and then realize how it comes. Examples of linear combinations. Alright, we will now deal with linear combination. So, we will deal with two vectors here. Two vectors V and W, and two numbers, any two numbers, two real numbers actually, C and D, and we will consider different values for C's and D's. So now let's see how we do this. So first, consider the case when C equal to 1 and D equal to 0. What do we get here? So the goal is to, and of course I should say, and consider the combination as we have shown, CV plus DW. Okay. Now what is this CV and DW look like? Well, 1 times V plus 0 times W. I know this is that V1, V2, it's 1, it just gets multiplied. On the other hand, when you talk about 0, 0 takes the place of D, and now 0 times W1, 0 times W2, which means you have V1, V2 and 0, 0. Again, I'm going to explain something. V1 plus 0, V2 plus 0 is V1, V2. So that's all we got. We got V1, simply, which is equal to V. So now look at that. So just because we have here 0, it eliminated W. And if it is 1, it's as good as not writing anything right next to V. So it's like other algebra. So one thing is important to realize, that the 0, just like in real numbers, we have this 0 vector, which is also a very special vector. This is called, any other vector that's not all of them are 0 are called non-zero vector. So I'll call it 0 vector. It's called. Any other vector that is not both 0 are called non-zero. Let's look at another example. When C equal to 2, D equal to 0. So in that case, you have 2V plus 0W. So we know this, we have seen this, it can be eliminated. So 0 vectors is as good as not adding, because you see it gets absorbed here. So you have essentially 2V, that's it. We know what 2V is, how to deal with it. Simply add the internal numbers twice. So now let's look at C equal to 1, D equal to 1. In that case, you get ordinary V plus W, because this 1 and 1 here, you can, like here before, we can avoid writing that 1. It means it's already 1. Now let's talk about C equal to 0, D equal to 0. 0 times V plus 0 times W, and you have 0 vector plus a 0 vector. This is denoted as, we can denote it as we can denote it as 0 vector. Okay. So 0 plus 0, again, you can show that it's just the ordinary 0 vector. So that is interesting. So is there anything else we can think about here? So essentially, what we can now do, let's say, what about if we go about, say, C equal to 1, D equal to minus 1. In this case, you'll get 1V times minus 1, or D is minus 1, W. You essentially get V minus 1 goes up, and essentially you can say this is this. So whenever you have minus in front of it, that means you are multiplying by minus 1. This is essentially the subtraction. Is also a linear combination. So you see, by coming up with this extra rule of linear combination, first you define scalar multiplication, then you define addition, you are able to create lots of new vectors. Now you might say, what is the big deal? The big deal is that when we solve real problems, you need a variety of types of things to represent and create to do your analysis. And that's what we are able to generate this machinery. These two little rules we can use over and over without knowing anything much about other things. We can create it. So now let's look at one more example. C equal to 0, or maybe C equal to minus 1, D equal to 0. So minus 1, 0W, which you simply get, this one vanishes, it becomes 0 vector. This you can simply write minus, as I said. The convention is that you assume that there is a minus, and then 0 vector, minus B. So again, I want to emphasize, this means, this is a symbol for saying there is a minus 1 multiplying. It's just a convention, you put a minus in front of it. So this is to be realized. Okay. It also means something else. We are not going for, in higher abstraction it's different. We are not worried about group theory and all, but let's think of it this way, in simple rules, in terms of. So now, so far so good. So let's do one final thing. Let's say with real numbers. Say I have C equal to 2 and D equal to 3, and I have V equal to 4 and 2, W equal to minus 1 and 2, and I'm going to do CV plus DW equal to 2, 4, 2, and D is 3, minus 3 we want to take. So let's say minus take 3 to make it more interesting. Minus 3, and then you have minus 1, 2. So now you can apply scalar multiplication with these. 8, 4, 3 minus 6, and now you apply vector addition, and then here you do scalar multiplication, and what do we get? Now after using vector addition rules, we will get this nice 11 minus 2. That's what this gives us. So essentially we can say 2V minus 3W, because this means again multiplying by minus 3. I'll make it clear. This means again, essentially this is what it means. Whenever there is a negative sign, you think of that as multiplying with a negative number. Essentially we have defined only plus sign, the positive addition. We have not defined something called negative. Negative means essentially adding with the negative number or inverse. So this is the idea. So we have created a linear combination. But how about looking at it from a geometric point of view? Usually in vectors we talk about one dimension, which is just the ordinary number. Say this is also a vector of one dimension. A number, say we can say it's a vector but one dimension, or v1, that's all. So what we want to look at is, can we have a geometric meaning? When we talk about dimension, we tend to think about like physical dimension. Usually we can visualize up to one dimension, which is just one line, two dimension, which is like the flat, three dimension, that's dimension space we live in. But the thing is, we cannot imagine beyond three dimension, or rather draw or see with our eyes. So these are, concepts. You can draw analogy from the lower dimensions that we can see and make it abstract. Abstract in the sense that you generalize it. Although you don't see it, its mathematics that it produces helps you to do a lot of complicated calculations and solve your equations. So that's what, in a way, abstraction helps. So you make it powerful. You don't have to see everything to be able to solve it. You can solve it with pen and paper. So before we go there, we should take advantage of the 2 or 3 dimensions, things that we can see and represent vectors, and see how we can see it physically or have an understanding of it. Okay, so let's start with 2 dimension. Okay, 2 dimension. Maybe switch color here. Okay, 2 dimension. Let's consider 2 vectors. 4, 2, and I'm going to write -1, 2. These are the x, these are the y. Let's talk about, it's talking about x and y, and we will try to relate to coordinate geometry where we have x-axis and y-axis. Right? So here I have 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. Fine. So now let's talk about the first vector. What is the way, how do we represent? V, we represent it as, first 4 is x and 2. So you 1, 2, 3, 4. So this is the y-axis and this is the x-axis. Because it's 4 and 2, these, we need to go 4 steps to the right. It's going to be here probably. Maybe we need even more. 4, 1, 2, 3, 4 and 2. 1, 2. So put a point and draw a line from the origin, 0, 0. Okay. Let's put the negative axis as well, 0, 0, and call it a vector. This is how you represent vector. So essentially this represents V equal to 4 and 2. Okay. So now we talk about another vector, W, -1 and 2. So -1 along the x-axis, 2 is here. So that is our W vector, -1 and 2. So now let's talk about addition. Let's do the calculations here. V plus W is simply 3 and 4 that we have done. We know how this works, the rules of this addition. Well, what does it mean? Let's plot this one. 1, 2, 3 and 4 with 3 and 1, 2, 3, 4 along the y-axis. Right? So now we have found, let's use a different color to show the resulting added vector. So this is essentially the point 3, 4, and this is essentially V plus W. This is the vector, and let's draw it. Now you'll see that essentially, of course, I'm not able to draw it to nice scale. Maybe it should go up to this. Essentially, this is, you can think about being parallelly transported along this. You take this. Let me use a different color to show you the mechanism of it. I'll use blue. So essentially you can think of it as like first this and then move this way over here, and so that its tail meets the end of the first one, V, which is W, and you start moving parallel along this, and wherever it meets, that's what. Or you can do this, take this as the first one and move this instead, you'll arrive at the same point. So that is the resulting vector. So you can think of vector addition as this operation. Okay. So also let's look at minus. Although we know that vector subtraction is just taking an inverse, how is it going to look like here? So let's draw it here. Say we want to do v minus w here. We know from our simple calculations that this is essentially minus 1, 2, 5 and 0. Let's draw it the same thing again. One, 2, 3, 4, minus 1, minus 2, 1, 2, 3, 4 along the y-axis. This is the x-axis. So now we know the first vector v where it belongs and w as well. Let's write them where they belong. 1, 2, 3, 4, 1, 2. Here this is the first one, v, and this is the w. Here I'll not draw all the coordinates. Now because it's a negative, what we do is that, what is the negative of this vector? This means essentially what, minus 1 times w1 or minus w2. What is in w1? w1 is minus 1 times minus 1, because this is what w1 is 1, and the other one is 2, so it's minus 2. So this vector is going to be 1 and minus 2. So we have to have here 2, 1 and 2. So this is it, 1 and 2. So essentially it's in the opposite direction. I'm going to write with red color. That's it. That's minus w. And now you add it. Once you add it, you again plot this 5, 0. 1, 2, 3, 4, probably 5 would be here. And 0. 0 means along the y-axis, it's the same place. So essentially 5, 0. So you ended up with this vector. And how did you get it? By adding these two, v and minus w. So that gave you this vector in this parallelogram. Say, I'm going to redraw it to scale properly a little bit, at least try. That's what you are getting. So this is the interpretation. So we can see now the negative as well. So and this v minus w, you can say it's 5, 0. So that is the interpretation of vector addition in this. So sure, we have seen two-dimensional vector so far. What about three-dimensional vector? Maybe we can apply the same kind of intuition. Let's see what we get here. So in this case, we will show that three-dimensional vector can be generalized in a very similar way. 3D vector represented. So let's consider a vector 1, 2, 2, and another vector w, which is 2, 3, minus 1, and we add them, say, and you do the same thing, add component wise or position wise. 1, 2, 2 plus 2, 3, minus 1. So you get 3, 5, and I think we have here 2, right? This is 2, 1, right? So of course sometimes we might be able to, as I mentioned, we can write these vectors as this. It makes the notation clear. But let's try to represent how would it look like on the actual, three-dimensional drawing, right? here. I think we have here. Okay. So now let's draw this in red, the coordinate in red. We have this, maybe. This one we call this x-axis, y-axis, and z-axis. 1, 2, 3, 4, 1, 2, 3, 4. So we have here 1 and 2, 1, 1, 2, 3. Now how do you represent this vector here? So we'll use different color. So this is 1. So you walk along x-axis 1 unit of time. Then you go along 2 along the y-axis. So sure, let me see if there is a negative number involved here. Maybe that would make the explanation more interesting. Yeah. So let's not worry about this vector, but I want to use a more interesting vector. So I'm interested in plotting vector 1, -2, and -2. That is more interesting. 1, and I would like to do -2 along the y-axis. So that means I need to extend my y-axis in the other direction as well. Let's do that. -1 and -2, right? So after that, I want to show you that we walk along y in -2 direction steps, and then so we started our journey here, we reached there, and then we move along this, and then we straight go up 2 steps. So this is what it is, 2. And here is the final point. So we have gone along x direction, y direction, and z direction. That's our point, which is our 1, -2, and 2. Now you draw a line from origin to the end, and this is your vector representation in 3D. So that's essentially the 3D representation. Now finally, we are going to show you that you can do linear combinations on 3D vectors as well. So use same way. Of course, in this case you have the same scalar multiplication rules and then vector addition. So linear combination with 3D vector. And by the way, you can do linear combination with vectors of any dimension, not just 3 components. So let's say v equal to 1, 0, 3, or you can write it as, if it's too difficult to, so this, or you can say okay, that's one we can do. Now we can do linear combinations again. Say I want to do, say, 2v 3u, no problem, you can do that. 2, 1, 0, 3, or 3, 1, 2, -1, and again do the same rules. 2, 0, 6, scalar multiplication rule, 3, this is 6 -3, and then you add up component wise using vector addition, and you will get 5, 0, 3. Okay, so far so good. So what about much more complex things? So you can add as many terms as you want. So if you had, suppose, one additional vector, say w is another, and you had 3 numbers c, d, f, then you could do c, v, u, v, d is u, f is w. So you can keep adding several, but finite number of time, a few of them, like 10, 15, not like infinite number. So something. So you can add any number of them. These are also linear combinations. So we have shown you the concept of vector, the motivation, and how to represent it. We moved from 1 to 2. 1 is essentially ordinary number, scalar, 3 dimension, and how you can keep extending the same idea to many dimension as long as you have many elements, first, second, third, fourth, fifth element, as long as you want to have it. Of course, we'll use it in the next lecture where we will discuss length and dot product, and we'll first introduce by showing you what is a many dimensional vector or any, and we'll explain more about it in detail. Thank you.